Gravity Basics Part 2. We will assume that all spinning planets have the 3D shape of a perfect sphere. In reality, spinning planets, for example, Earth, are oblate spheroids, which means they bulge out a little bit at the equator. But we're going to assume that we always have a sphere unless we're told otherwise. Into these figures, let's draw how the gravitational field lines would appear in the vicinity of each of these two figures. So if we have on the left a faraway view of a celestial body, gravitational field lines point in the direction that a gravitational force would act on a mass if you put the mass at that particular location. Gravitational field lines are going to point toward this object like so. The fact that the field lines are far apart, right where my fingers are now, compared to right here at the surface where the field lines are closer together, that indicates that the strength of the field further away is weak, and the strength of the field closer to the surface of the planet is stronger. Now, if we're up close, isn't it true that up close, these field lines look like they're pretty much parallel to each other? In other words, they're spaced equally far apart right here at the surface, pretty much as they are somewhat higher up, which means here on the right, G is basically considered a constant. It doesn't change hardly at all when you make changes in elevation relatively near the surface of a planet. On the other hand, like on the left, when you see an entire planet and we are moving things closer and further to the planet on the order of the radius of the planet, then G cannot be considered a constant. And that is going to be important because depending on which case we have, that's going to determine what type of equation we use. If we have a faraway view of things, if we're talking about celestial objects, then the force of gravity equation that we're going to want to use is big G times one of the masses times the other mass divided by the distance between them squared. On the other hand, if we're up close, as we have been in much of this course so far, and you might have been in your first year physics class, to find the force of gravity, didn't you just take the mass and multiply by 9.8 or 9.81 or whatever your teacher suggested you use? Or what we've been doing in this series of videos, usually we use 10 for G. If we're up close to the planet, you can use this simplified version. If you're far away, you have to use this. Similarly, let's start with another one that you are used to. If you're up close to a planet, gravitational potential energy, isn't it m times G times H above some reference line? Simple equation, m times G times H. But if you can see the whole planet, and you're starting to talk about satellites, for example, going around the planet, you cannot use that simple gravitational potential energy equation. You have to use the absolute gravitational potential energy equation, which looks like that. We're going to run into this kind of thing that's right in the middle of your screen in this series of videos. One more thing before we shut this down, just so that it's out there, the value and units for the universal gravitational constant, also known as the Cavendish constant, big G, 6.67 times 10 to the negative 11th to 3 significant figures. And the units for it, we could prove this to you, but we're not going to right now. In order for this to work out in Newton's law of gravity, the units of G have to be that, Newton meter squared per kilogram squared.